This is old news. Linear quadratic. I say old not in a disparaging way. It's just that we've spent about 2 or 3 weeks maybe in those types of modeling. This is what Usain Bolt is going to look like to some degree. As a subset of quadratic, we'll look at cubic modeling. Okay? So, this data though, if you, what's that? You can look up there too. Your shape of this data, if you look at this data right here, like we did last time, and you take a scatter plot of this guy, which we'll do right now.
Do we put the 2, 0, 2, 1, 0, 0?
Oh no, that's old data, Linda. Sorry, that's from yesterday in my 244. Just L1 and L2. Make a scatter plot, yeah? If you need it, you need a little booklet, exactly. The little booklet comes in handy. If you need it. Turn that off. Gesundheit. And we spent a great deal of time last time with this graph. Our graph looked kind of like this graph. And eventually we settled on the fact that, Aaron, what's the matter? What's the matter? What's up?
I have weird lines coming from.
Oh, just turn your Y equals. That happened to me too. If you have weird lines coming across, just press your Y equals button and turn off any equations you have in Y1, Y2, Y3. They can get in the way. We're going to add a new curve to this in a second. Okay? Now, we had a discussion last time about the shape of this. Yes, we did. We had a discussion about the shape of this. And the discussion was interesting. We decided that we put a quadratic fit to this. But what was the problem with the quadratic? Remember what happened with the quadratic that we didn't like?
It went back up.
It went back up, yes. It came down, it fit kind of nice, and then it went back up again, so I don't know, that didn't make a lot of sense. So if we were to extend this pattern out, it wouldn't fit very well. It wouldn't fit very well. Good, beautiful, quadratic. Then Hassani tried cubic, which was pretty slick actually. But something cool happened with the cubic. Do you remember? Remember what happened with the cubic? It did that cool like shuck and jive, like it came down and then jumped up and then jumped down again, which implies that somewhere over there we should actually be seeing like a resurgence and then a drop of the number of heads, or number of tails, I guess, which doesn't make a whole lot of sense because they're decreasing on time. Now the deal is, and this might not be obvious to you guys, this is a perfect example of what's called exponential modeling. And that's what I want to talk about. Yeah, we got some time to talk about that today. Exponential modeling. Now, the reason we can just jump right into it is because Mike has already decided, and some of you probably picked this up too, when he noticed the 12, 6, 3, that pattern 24, 12, 6, 3. Yeah, Tori's like, yeah, it's half and half and half and half. So what you can do is you can look at the actual data in some of these data sets. You can look at the data in some of these data sets, like for example, we'll use the pretty one right here. We'll use the pretty one right here. And realize that there is a really nice pattern at work. To get from 24 to 12, you divide by 2. 12 to 6, divide by 2. 6 to 3, divide by 2. 3 to 2, divide by 2-ish. Right? There's an ish. I mean, there's definitely an ish at work here. There's lots of ishes at work here because it doesn't work perfectly. It doesn't work perfectly. But when you start looking at the averages of the data, that division by 2 is actually pretty close, yeah? Pretty close. It's off. It's ish. Definitely estimated. But it's close. So what I want you to do is I want you to think about that over here on that graph momentarily. And I want you to see why the old models that we have don't fit this based off of that assumption of repeated multiplication. So this distance right here, let's just call that distance d. Just for lack of a better term, let's just call it d. Okay, and we're going to do this. We're ishing this. What's this? What do you think that distance should be?
Half of D.
Half of d. Yes, that makes sense. Yeah. Whatever this was, that should be about half of it. That's what Michael was saying. When 24 goes to 12, that's half. And the 24 and the 12 are y values. So this should be half of d, yes? Good, good. Should we call that something else like e? I don't think so. I think we should just call it half of D. And Tori's like, please stop with the variables. What should we call this?
Half of.
Right, thank you. Half of D, aka a quarter of D. Yes? But I like the half of half. That's very, very nice. Half of half. Because it's half of that, which is half of that. So this guy should be about a quarter of this altogether. This is giving me nightmares about our hot tub right now, trying to get the chemicals balanced in that thing. They got 300 gallons. You saw the picture of Max in it. 300 gallons of chlorine, bromine. How about this? What should this be? I hear an eighth, and I also hear half of a half of a half. Which is 1/8 D. And then I think we can see where this pattern is going. The next one will be 1/16, which is a half of a half of a half of a half.
Never hit zero.
Very nice. It'll never zero out. That was the problem. We had a bit of a modeling issue last time. We'll fix that today. We'll fix that today easily. But the trick with this is, every successive y value becomes half of the one before it. So the next will be half of a half of a half of a half of a half. It's going to get annoying to say that over and over again. So instead of saying it over and over and over again, we're going to say 1/2 to the blah power. So for example, turn it off. This guy right here is 1/2 to the first power. This guy is 1/2 squared, 1/2 cubed. And notice that the power matches perfectly with how many trials we're on. After one trial, we've taken half of what was before us. After 2 trials, we've taken half twice, half of a half. After 3 trials, half of a half of a half. And so forth and so on and so forth and so on. So there's really 2 things at work here. There's 2 things at work here. There's this D value, which is how many people are in the room at the beginning. And then there's the number of times we take a half of it. Is everybody seeing that? There's kind of 2 things at work here. And those are the 2 components of the exponential model, the so tight. Those are the 2 components of the exponential model. To predict a given y value in an exponential model, you got to know 2 things. You got to know 2 things. Number 1, you've got to know, and math books usually call it A, which is the base value you start with. It's the base value you start with. Then you've got B, which is the fraction or multiplier that you're using to repeatedly multiply. So for us, this would be a half. This would be a half. We'll come back to that momentarily. And the variable goes up here. That's the difference. That's why we call it an exponential model. Because the variable is actually the exponent. Think about why that is again using our example. Think about why that is again using our example. All right? Using our example, that's how many times multiplied by a half. Once, twice, 3 times. Well, since we're using it to measure multiplication, it has to be an exponent versus a coefficient. If it was a coefficient, it would be plus, 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 like a linear. But it's multiplication, so it's exponential. A half times, a half times, a half times, a half times. Fair enough? Now, these 2 guys often have names. They often have names. I'll throw them in quotes for you in case you see them in your textbook. B is often called the base. A is often called an initial value. And they're fine terms. They're totally fine terms. They're totally fine. Nothing wrong with them. But more important than knowing what they're called is knowing what they're doing. What they're doing. This guy right here, this A value, is how much you start with. Now there are 2 kinds of exponential behavior. This is called an exponential decay model because the data is going like this. If we have time today, which I think we will, we'll get into an exponential growth model where it actually turns around and goes the other way. Because that can be more interesting for you guys. And we'll take a look at that as well. Okie doke? All right. Now, next thing, I want to use our TI to regress the equation. Now, chances are you can figure out what the equation has to be based off the averages of our data. But the equation that we get off of our data is going to be an imperfect best fit line. We can get the theoretical, yes? What is our A? What is this A that we're calling our initial value?
Isn't it?
It's 24, because that's how many we started. It's this, I called it D up here. I apologize for mixing variables up. I called it D, but that initial height is 24, yes? 24. And what's the B going to be for us? 0.5 or a half. That's the perfectly theoretical model. What I want you guys to look at is, can the TI predict that based off of this data?
Why would that be 25?
Why would it be 25? No, 0.5.
Okay.
0.5 for D, or 1/2. 1/2. What I want to do is I want to use the TIs to see if the TI can actually find that pattern in the equation. Because you can't always just look at data and be like, oh, it's exponential and here's A and here's B. We can do it here because we know what the points are doing. So grab your TIs. I'm going to erase all this out of here. Erase all this out of here.
Snap.
Good, yes. So grab your stat, go to your calc. We've already explored lin and quad reg quite a bit. We'll skip over cubic and quart. They're fun. They're fun, but they're not crucial. I don't know why this one's even on there. We'll skip over that too. Natural log reg, you can skip him. EXP reg, that's the one you want to use. EXP reg. So grab him and stick him in Y1 like you usually do. So go to vars, Y vars, function, Y1. Hold that thought.
Wait.
Hold that thought. We're doing the same thing we did with linear regression, except we're picking a different regression. Still putting Y1 like we've always done. When you press enter, notice you get an error. Who's not getting an error? You didn't get an error, Shelly. That's interesting.
I don't have an error.
Good. We should get an error. Yes, we should get an error. And here's why. It has to do with something Benji said earlier. The problem with our data and this model, this equation can never, ever, ever literally equal 0. You keep taking half of half of half of something, it never zeroes out. But our data does, yes? That last data point of 7 and 0, pull that off. Hit quit. Hit quit. Go back to your data. And get rid of the 7, 0 data point. Delete. Delete. You don't. First one's okay. First, hang tight, hang tight. Pull the 7 and the 0 off. You know? Now, Tasani, exponentially, think about y. You're plugging in 0 for x. If you plug in 0 for x, what's b to the 0 power? 1 times 24 is just 24. So mathematically, it's valid. The problem was, the 7, 0 was saying if I put 7 in here, I need to make that equal 0 over here, and that's the issue. That's the issue, yeah? That's the problem. Okay, cool so far? Everybody understand the mathematics, the mathematical logic behind pulling the 7, 0 off? Decent? You can't ever have an exponential model ever go completely to 0. Now think about why our data did 0 out. And eventually you will 0 out. If you give somebody a coin and say flip it until you get tails, eventually they're going to get tails. But can you predict how long it will take with 100% certainty? No, I could theoretically have given somebody a coin today in class and said flip, 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 and they're still flipping right now. Is that likely? No. According to that bell curve I showed Mike earlier, it's definitely not likely. But it's possible, and that's why the model doesn't like the zeroing out. Okay, cool? Let's do it. Oh, I need to do second enter, I guess. There we go. It's thinking about it, it's thinking about it. Take a look at these values. Take a look at these values. A, 24.2.3. Damn close to what? 24, which is the theoretical that we knew, yes? We knew the theoretical of 24. The TI didn't know that. But he could look at the averages and be like, it's going to come closest to this point. Check out that B. 0.47, which is damn close. It's almost what? It's almost half. Hey, graph! Let's see how it looks. And what doesn't it do with that the cubic and the quadratic did? Right, well it doesn't hit 0. Nice, thank you. It doesn't hit 0. It also doesn't rocket back up. It keeps getting closer and closer to 0 the further and further it goes out. But it never ever will actually hit 0. It never and ever will actually ever hit 0. Because it can't. There's always that chance, probability again, Ariel. There's always that chance that we could take 32 times to get heads, or 63 times to get heads, or 123 times to get heads. It can always take one more time. 50-50 each time. This indicates that beautifully, yes? This indicates that beautifully. Is that fair? So it's just one more type of regression. But the beauty of all three of these is that it forces you to kind of think, okay, why does one make sense over the other? Why does an exponential model make sense? Well, because of what Micah said. And hopefully some of you guys noticed as well. When you're looking at your raw data, you noticed there was a neat pattern. You noticed there was a neat pattern in the y values. It's different than linear or quadratic type data. Let's compare and contrast, shall we? I think we should. We're going to turn this off momentarily. And we're going to make up some linear models here right quick. Let's just compare and contrast. So, let's look at a linear and a quadratic model. Let's make it real simple. Make it real simple. Y equals 2x. Yeah, that'll work. What's a simple quadratic? Y equals, how about x squared? That'll work. It's real simple. Doesn't matter which one you use, the patterns are the same. Take a little t-table here. X and y. X and y. And let's just start at like -2, -1, 0, 1, 2, 3, 4. Do it for both of them. -2, -1, 0, 1, 2, 3, 4. Fill out those y values. Fill out those y values for both of those models. Turn this off momentarily.